You probably already have seen vectors, so you probably have seen calculations like this where you do the scalar multiplication and then you add them together. 1 plus 6 is 7, negative 2 plus 3 is 1. And this is something you already have seen in physics or calculus 3. But rather than only limiting ourselves to these concrete examples, it's very helpful if you think about the properties of vector spaces over some scalar. Here we have these real numbers, right? But sometimes you can also have scalars as complex numbers too. And I want to talk about this properties of vector spaces over some scalar field R or C. Now the reason that we want to do this is so that anytime we see a mathematical object that satisfies these properties, we want to call that vector space. And if you have vector spaces, then not only the similarity to these concrete examples can help you think about them, you see a lot of theorems or concepts that you know about regular vector spaces can carry over to these abstract vector spaces. That's why it's so useful. And in fact, in partial differential equations and many other areas of math, it turned out to be a very fruitful idea. So let's try this. If you have two vectors, you can add them. Okay. If you have two vectors, u and v, you can add them. They'll again be a vector. So in other words, the vector space is closed under this vector addition. And vector addition is associative. You probably have seen this in high school algebra. It's associative. Yeah, vector addition also enjoys this property, associativity. And then there's also identity element. So if you have a zero vector adds to any vector and it doesn't change the vector, gives you the same thing. That's called the identity. And then you also have the inverse, the additive inverse. And if any mathematical object satisfies these four, you call that a group. In other words, vector space is a group under addition. And then there's an additional requirement that it has to be commutative. And if that's also true, then you call this thing a commutative group. So vector space is an example of a commutative group if you only consider its addition operator. But we also have the scalar multiplication, right? So let's talk about what happens to scalar multiplication. Well, any element, any constant number can be multiplied to a vector. So if you have a constant number and a vector, then you can do a scalar multiplication. So that's called scalar multiplication. And we require that if you happen to choose 1 from the scalar, 1 times u should be u. It has to be like a multiplicative identity in the scalar field. Then we also need distributive property, which says if you have this constant as before, if you have two vectors, then it should be cu plus cv. And lastly, the distributive property works the other way too. If you have c plus d times u, it should be same as cu plus du. Okay, looks like a lot. We wrote down 9 properties or 9 requirements a mathematical object should satisfy in order to be called the vector space. But in fact, because these are so common in many operations that we use in mathematics, many things turn out to be vector spaces. So let's talk about some examples. Well, R3, where elements look like x comma y comma z, is obviously a vector space with the vector addition that if you have a, b, c, you have a plus x, b plus y, c plus z, and also constant multiple to a vector can be calculated this way. So with this scalar operation and with this addition, R3 becomes a vector space. So really what people say is R3 equipped with the addition and scalar multiplication is a vector space. That's just an abstract way of saying something that you already know. Slightly non-trivial example would be C, the complex number over R is a vector space, because if you have A plus BI and C plus DI, if you add them, if you add two complex numbers, we know that it also gives me another complex number, right? And then any constant can be multiplied to A plus BI, where C is a real number. If C is a real number, then that gives you C times A plus C times BI. So that's again a complex number with the real part being CA and a complex part being CB. That's still somewhat trivial. Let's talk about some really non-trivial example. Non-trivial example will be something like this. C 0, 1, and this is space of continuous functions over the interval 0, 1. Okay. So in other words, here's 0, here's 1. Think about any continuous function that you can draw. Okay. Now, if you have any two functions, fx and gx, belonging to this C01, let's just call it C for short, then what's the sum of two continuous functions? Well, if you have one function like that, another function like that, if you add them up, you get a bigger function there, but that's still continuous, right? So we see that addition is defined, and not only that, if you have a function and any real number, constant number times fx will still give you another continuous function. So with this scalar multiple and this addition, this becomes a vector space. Now, actually, the most useful kind of vector spaces are of similar forms. So let me talk about another thing called L2 space. L2 space over, say, 0, 1. And often I think people write this parenthesis over the interval it's over. Now this is a collection of functions. We collect all the functions that have the following property. If you integrate this function, you take the absolute value of this function, you square it, and if you integrate from 0 to 1, it has to be a finite value. Now for this one, it's actually harder to think about what's not in here than what's in here. Let me give you an example. If you have, say, 1 over square root of x, that won't be in here, because if you square this, it's 1 over x, and if you integrate from 0 to 1 of 1 over x dx, that's ln of x, and if you plug in 1 and 0, log of 1 is 0, but log of 0 is negative infinity. So if you calculate this, this gives you infinity. So this is an example of a function that's not in L2. And to prove that any two functions in this space, the sum is again in this space, and also the constant multiple. The second one is kind of easy, but this first one, you need something called Cauchy-Schwarz inequality. So it's not that easy. But just trust me, it is a vector space. Okay, so hopefully these non-trivial examples might have given you some motivation for studying vector spaces as an abstract object. But now let's think about what are the things that we know how to do in regular vector spaces and how we can have similar things in infinite dimensional vector spaces. So first thing that you know are something called bases. Okay. In the case of two-dimensional vector spaces, 1, 0 and 0, 1, a lot of times these are called I and then J. These are called standard unit vectors. And the reason we like these and we want to call them as standard unit vectors is because any other vector, 3, -5, for example, can be represented as 3 times 1, 0 plus -5 times 0, 1. So you can write it as a linear combination of these two vectors. Okay. Not only that, it's the smallest set you can come up with. So in two-dimensional spaces, you'll see that the least set of vectors that you can use to represent any other vector will have to be at least 2. Okay, you need at least 2 vectors to represent anything in two-dimensional space. So in general, we call a basis B of a vector space V as something that satisfies 2 requirements. One is that these are linearly independent. Okay, in other words, it's not true that if if you have one element in B, U cannot be expressed as V, W, eta, whatever. So C1 plus V. You cannot express U as linear combinations of other things in this B. Okay, so it's linearly independent. Linearly independence means that you cannot express one as linear combinations of a combination of other elements. Okay, and second is that anything in V has to be in a span of B. Okay, so span is like collection of all linear combinations. So I mean, in this example, it's kind of clear. Any element in the two-dimensional vector space is a linear combination of these two. So this means that anything in the two-dimensional space belongs to the span of I and J. Okay. All right. So let's think about another basis. Here's another basis for 2 by 2. So think about 1, -1. And then, let's see, 0, 1. All right, that's a little strange, but it's still true that any kind of vector space, any kind of vector in this two-dimensional vector space can be represented by these two as linear combinations. So let me just call this as U, and let's call this as V, and it works like this. If I choose 3, -5, and I wanted to write this as some linear combination of U and V, you can say it's 3 times 1, -1, and then let's see, it requires -8. Okay, so -8, 0, 1, right? So if you multiplied it, and add them up, you'll see that it's same as this. So it's really 3U plus -8V. Now, it may be helpful to think about something that's not a basis. So this is not a basis. Here's an example. U equals to 1 comma negative 1. V equals to negative 1 comma 1. Well, in this case, they just happen to be negative of each other, so U is equals to negative V. That means they're not linearly independent. Okay? One depends on the other in a linear fashion, so they're not linearly independent. And in fact, if you try to represent 3 comma negative 5, then you're going to quickly find out that there's no number here you can put in so that this equality is satisfied. So let's ask this question for one of the non-trivial vector spaces that we learned. And this is actually a really hard question. It's like we were going at 5 miles per hour, but now suddenly we are going at 100 miles per hour. It's a sudden change. So even though I'm going to provide you with an answer, I won't be able to exactly explain why that's true. But nonetheless, this should be a motivation for learning abstract vector spaces. Okay, so let me put the question. What is a basis for this L2 space? Now we talked about the L2 space over the interval 0 to 1, but let's talk about negative 1 to 1 because it's easier to write. By the way, to recall, this means that you have a function whose absolute value squared, and if you integrate from negative 1 to 1, it has to be some finite value. Now, it's a little silly because we don't even understand what these functions are, and then we are asking what's the basis for this vector space. But nonetheless, the answer is the following. The basis looks like, well, first you have 1, and then sine n pi x, where n goes from 1 through infinity, and then also cosine n pi x, where n goes from 1 through infinity. So it's an infinite set. Of course, it should be an infinite set because it should be an infinite vector space. See, this is actually bigger than the continuous functions. And how many continuous functions are there? Infinitely many. But what do you think is the dimension of that vector space? It's even bigger than just a set of real numbers. So these spaces are infinite dimensional vector spaces. And if you think about it, the number of elements in a basis is same as its dimension. So having infinite elements here, that means it's an infinite vector space. Now, although I can't explain what this means, I can still explain the outcome of this answer. So in other words, this is what I'm trying to say. If you have any function f of x, which is square integrable, and that means that this is a finite value, okay, over negative 1 to 1, then it's true that that function can be represented as a linear combination of these functions. In other words, let's say a0, and then I wrote down sine first. I should have written down cosine first. That's the usual way people write. And pi x, then bn times these things. And since we have infinitely many of these things added up, we should write it as an infinite series. And what does this look like? This is what we call the Fourier series. Okay, so the very fact that Fourier series is true is why this answer works. Okay, these are equivalent things. To show this statement that any square integrable function can be represented by its Fourier series, the same thing as saying that the basis for this L2 space is this thing over here. Now let me just add a minor comment here. Often people put 1/2 here and put over 2 here because if you do it this way, then there's some inner product defined for this L2 space where all of these are orthogonal to each other and their norm is 1. Okay, so that actually brings us to what a norm is. Well, we have to talk about something called the inner product, which we usually say dot product rather than inner product. And some books even distinguish their meaning, but I'll just use them interchangeably. So what's a dot product? It means that if I have x comma y and then a comma b, the dot product is ax plus by. That's what dot product means. And actually, if these are complex numbers, then you have a version where, so there's something called a Hermitian inner product. Hermitian inner product. That if you have a comma b and c comma d, and the dot product is defined as a c bar plus b d bar, where this bar is a complex conjugate. You know, complex conjugate means that the I is replaced by negative I. So x plus yi gives you its conjugate. Right? And you do this so that it satisfies some positivity condition. All right. So hopefully at least you've seen this one here. And again, we're going to talk about its properties. What are the properties of a dot product? Well, first, the properties of dot product. First, if you have properties of dot product or inner product, if you have u and v, two vectors, their inner product, this is commutative for vector spaces over R. Now, if you have a vector space over C, complex numbers, then the rule changes to give you this complex conjugate. Okay, so there's this some complications when you work with complex numbers. And then there is the distributive property. And you can check that these are all true in the regular dot product that you're used to. And also it's linear. Actually, if you have AU and then V, that's same as A times U V. Okay. Now, because of this conjugate here, in the case of C, this is slightly confusing. If you have U times AV, and this A is a complex number, then this is A bar UV. So that's kind of forced because of this condition here. But if all these extra thing about complex numbers is confusing, just don't worry about it. Just think about only these properties. Okay. So these are some properties, and moreover, the important thing is that if you have UU, then it has to be non-negative. Okay, and you know, in many cases, it happens that 0, 0 is the only possible 0. So 0, 0 will give you 0 for the dot product. But there are some example vector spaces where this is unfortunately not true. But in most cases, this is what we will have. Right? Okay, so for L2 spaces, what is the inner product? Well, if you have two functions, fx and gx, then integrating a to b of fx times gx, and if you define this as your, just define fx and gx as this integral, then this satisfies all properties of inner product. And this integral is not just defined for L2, but it's also defined for continuous functions. So in that space also you can think of this as an inner product. So when I said before that this set over here is orthonormal, it means that, well, if you have an inner product, you have the following thing. First, you can talk about the norm of any vector as the square root of u inner product with itself. Recall that's true, right? If you have a comma b in two-dimensional space, what's the norm of this? This is really square root of a squared plus b squared. That's exactly the same as a comma b dotted with a comma b, and then you take the square root, right? So this is always true. So that's the norm. Second, the angle is, you can even define angle as the angle theta will be cosine inverse of u dot v divided by u and v. You see this familiar one. Usually you don't really think about angle between two functions. That's kind of silly. But what's still really important is the fact that if u comma v is 0, we say that u and v are orthogonal. Okay. So once you have an inner product, then you can talk about its norm, and you can also talk about two vectors being orthogonal to each other. So this set being orthonormal, meaning that every element is orthogonal to one another, and all the sizes are equal to 1, all the norm is equal to 1, it makes sense. You can actually check that it's true by plugging these functions into the inner product that we just defined.